Okay, so let's start with a review of what we did in week 1. Okay, so we started by considering classical field theories. And the basic example that we studied was the Klein-Gordon theory, or a theory of a scalar field, which had a Lagrangian density of the form given by this. We solved the Euler-Lagrange equations, and we found a very simple expansion. We basically found, so this was a prototype of what we call a free theory. We were able to solve it completely, and up to factors of 2 pi that I'm going to define to be 1 for the time being, we found something of this form. Where here k dot x meant k0, t minus x, or k dot x, and k0 is also wk, and they are defined to satisfy the relation k squared equals to m squared. Okay, where k squared is a norm, is a 4-dimensional norm. Sorry. And this was in the classical field theory. So phi being real implied that this had to be the complex conjugate of this. Okay. Then we moved on, and we said we want to quantize this theory. And we did something called canonical quantization. Once again, we did it for the Klein-Gordon theory. And in the end, we can summarize everything by saying that we found our fields. Now, fields became operators. And after a lot of work, we can say that all we did was to really replace. Let me actually do something here. Just for fun, I'm going to write the 2 terms individually. All we did was to replace a star by a dagger. Okay? And we interpreted this as being annihilation operators, and these ones as creation operators, which then had commutation relation of this form at different case. We define Hilbert space basically by postulating the existence of a vacuum state, defined as a state that is annihilated by all the annihilation operators. And we created states in the Hilbert space by acting with creation operators. Very good. Nothing fancy. Now, I think we defined them, but don't quite remember. And if we did, we probably, so this is just a matter of notation, but it's convenient to call this and I'm sure I'm going to get it wrong if I. So phi plus the piece that only has annihilation operators. Or in a sense, we can think about this as being a piece that has negative frequencies. So we interpret that as having annihilation operators. And this piece over here which has the positive exponential, is called phi minus. So I think that the notations in Preskill and Peskin and Schroeder are actually conjugate of each other. Okay, so for today, I think we're going to follow Peskin's notation, which is phi plus and phi minus. Okay, very good. So this equation told us that this theory was basically a theory of, so this is we said that this is a free theory because the commutation relations told us that these are basically a set of decoupled harmonic oscillators. Okay? So even though it was a free theory, we found an object that we also found in QFT0, which was at the heart of unitarity, if you remember. So the object we found was this Green's function. Which you guys had to compute explicitly. Well, it was an optional problem. I hope most of you did it. Okay? And what is this in terms of expectation values? Do you remember? That's right. So this thing was this object. Which we decided to give a name to this operator, to the way of writing things like this. We decided to give it a name, and we said that it was the time ordering operator acting on these two fields. And this is what we got, okay? So now that we're discussing this, let's use a chance to rewrite this a little bit, okay? We're going to use this decomposition. So phi, the field phi, is going to be decomposed in phi plus and phi minus. Okay? Let's do it. So what do we get? You get that this, which is equal to this, is equal to this. Now we're going to use the decomposition, right? So phi of x is going to be equal to phi plus plus phi minus. But this is acting on the vacuum. So which piece survives? Phi minus. Likewise, here only phi plus survives. Okay. Yes, thank you. Very good. All right. Now we're going to do something a little bit sneaky, but correct, which is that we're going to add 0 to this. So I'm going to add the commutator, what I'm missing to produce a commutator of this object, okay? Of course, it's 0, because I'm actually going to get what I wrote before, which was a double 0, okay? So I'm going to write this as 0, the commutator of this, okay? You all agree that I have done nothing, right? This is identical to this, right? Because the extra piece vanishes identically. Okay. So I'm going to do the same thing here. And I'm going to tell you in a second why I'm doing this. The reason is that I hope you all remember that this commutator is just a number. It's not an operator, right? So if it's a number, it's something that can be pulled out of the expectation value, right? Now we can pull out of the expectation value everything that we have here, right? Because this is a number. So this is a number. This is also a number. So we can pull it out and say, well, this thing is this. Okay. So we conclude that our Feynman propagator is also equal to this funny combination of commutators. Now this means, right, that somehow there must be a connection. Well, just as we put it out of the expectation value with the vacuum, we can put it in back. We can put it back in, okay, if we wanted to. So we will conclude that this guy, as an operator, has a piece, which is this thing. So it might be nice to give a name to what this piece is. So there is a piece that we don't know yet, which vanishes when taken into this, but there is another piece, okay, which is exactly this, okay? And that's our Feynman propagator. Okay? So part of the job today is to find out what this extra piece is, so that this equality holds as an operator statement, okay? Yes. Just in the same way as when you have, well, no, maybe that's not a. So the fact that this is equal to this doesn't mean that this operator is equal to the identity operator times the propagator. The reason is that they can differ by something that vanishes when we take the expectation value with a vacuum, okay? Then this equality is just an equality. Okay? Very good. So that's what we want to find out today. Okay. Now let's move on. That's good. So let's move on with a review. The other thing we did, we said, well, this theory is a little bit boring. We're not going to be able to do many things with this, so we better introduce some interactions. And we said we have to introduce interactions in a controlled manner, otherwise we won't know anything that we're doing. And we said there will be a free Lagrangian plus a Lagrangian that contains interactions. The free Lagrangian, the prototype, is going to be again a Klein-Gordon, or it was a Klein-Gordon theory And this interaction, since we're in 4 dimensions, we're going to take it to be as a prototype again. This term. Can you spot any differences between this and the free theory Lagrangian that I wrote down over there? There are 2. Yes, M is replaced by M0. Exactly. Yes, I'm using different notations. It's not an accident. It's not that when I cross this blackboard, I switch to the it's actually on purpose. So last week, we spent some time studying the generalization to the interacting theory of the Feynman propagator. So we said, well, we want to consider this object. And we spent a long time actually computing what this was, and we got a formula that looks like this. So if we get I'm going to use z as the integral here because we have x and y already. But z here is a real variable or a set of real variables. Don't get confused. Don't think that we're doing something holomorphic. It's just that, well, after y, guess what? And then we have the exponential of the same thing. So, of course, here our contour is a little bit funny. It's a complex contour. That's where the capital T enters, or the calligraphic T enters, right? So it enters in the contour. So let's just... Oh, yes, sorry. Jumping ahead a little bit. The fancy, it's a fancy. Right. So the T, we have to remember, enters in the definition of the time integral contour. So our phi I actually behaves just as a free field. It has the same structure, if you remember. That's what we found. And the vacuum was also modeled to behave as that of a free field. Okay? So, if they behave like that, you know what? Let's see. A minus sign where? No, there is no minus sign. This is correct, right? Because it was minus IH interaction. But the Hamiltonian gives a minus sign when you, so you get the minus sign when you put the L. So, well, as I say, if they walk like free fields and they talk like free fields, why not think that they are free fields? So, we can, just like mathematicians, be happy because a mathematician would say that we have succeeded because we have managed to reduce the problem at hand to the previous theory. Okay? So, yes?
Just can you remind us what do you mean exactly when you say phi I behaves like a theory?
I'm not going to say it because we have done this. We have moved on. So, this thing, and I'm going to use my change of notation. I spent the whole night thinking about how to change notations. So I'm going to change it and say that this object in the interacting theory as a function, so thank you. Yes, well, by now you know that this is a common mistake. That this function, as a function of x and y, this is going to be just a function of x and y, right? Just a sign of x and y. I mean, it's the only thing that this thing is going to be a function of is x and y and lambda, right? So this object is going to be some function of x minus y, by the way, and lambda, okay? As a function, this thing is going to be equal to the limit when this goes to 1 minus I epsilon of a correlation function. Well, these things are called correlation functions. It's going to be some particular correlation function in the free theory. So note that I'm not putting the I anymore. I'm using now the notation for the free field. And now I'm going to go back to the particular case that we're considering as the prototype example. Phi for z divided by okay. Now, no signs whatsoever of anything here different from the free vacuum and our free theory. This is an object that we can compute in the free theory. Okay? It so happened that this function of x, y, and lambda, last week, we proved that is identical to this function of the interacting theory. Okay? So this is a very remarkable formula, right? In principle, we should be able to compute this completely, right? It's a free vacuum. We know how to expand the operators in terms of creation and annihilation operators. And we just have to sit down and do it. Okay? Well, as usual, this is easier said than done. Okay? If you try to do it, you're going to suffer a lot. In fact, we're going to do it in a very smart way that people develop, and still we're going to suffer. So if we just do it in the standard, by expanding all the fields that you see, well, of course, we have an exponential here. You might say, how do we do this? Remember that lambda is a relevant coupling. It's a marginal coupling. And therefore, what can we do with lambda? We get to choose what it is. So we can choose it to be very, very small, expand the exponential, okay, and then treat order by order in lambda and carry out this computation. And cross our fingers and hope for the best. Yes?
This might be a silly question about the notation.
Yes.
Switch to the other phi's, right? But shouldn't it be phi interaction?
Where?
Down there, in this line. Yeah.
Here? Of course not.
Okay, because it's the free one.
We have reduced the problem to the previous theory. Now, our job is to compute this object in the free theory. There is no phi interaction. There is nothing. The difficult thing last week was to show that this formula holds where phi interaction was a name given to this object that we got by taking a snapshot of the field, doing the thing that I said I wouldn't say that we did, which was to evolve it with the free theory Hamiltonian, right? That was a joke we made, that we were not supposed to say that, and yet I did, okay? And therefore, this phi interaction at all times behaves identically as this one, or is identical to this one, okay? So today, we're just going to concentrate on this and try to find ways of computing it, okay? Oh, but I remember now, well, I didn't remember, but it's in my notes. I asked you to generalize this. I asked you to generalize that formula to the case where we have any number of operators inserted inside the time ordering. And what did you get? You just got the same thing but with n of them inserted. Okay? Now, it's too early to claim that, but these objects in the interactive theory, these things that are called correlation functions, are the objects that contain all the physical information of your theory. And that's the reason we're going to work and learn how to compute them, okay? We will then have to do some work to actually extract the physical information, okay? So we will just have to work a little bit hard to achieve the two goals, okay? One is to learn how to compute them, and the reason we're going to compute them is that they contain all the physical information, and at this point, you have to trust me, basically because, well, this is the only object we know how to compute, so it better be the object that contains all the physical information. But it's actually true, and then we will have to work and extract the physical information from it. Okay. Now the time has come to actually find out what this is. Okay? Let's do it. To find the term in parentheses. Well, how do we do it? Well, there is only one way to do it, which is to work this out explicitly. So you have this. Now the time ordering tells us that this time we're going to have phi of x plus phi of x minus here, phi of y plus phi of minus here, times this object here. Okay? So let's go ahead and compute it. Well, the first thing is that if I want something that vanishes when I put the expectation value with a vacuum, right? I better rearrange these things in such a way that anything that has a creation operator goes to the left, and anything that has an annihilation operators go to the right. Okay? So let's start. This guy with this guy only has what kind of operators? I have to look here. Only has annihilation operators. So I don't have to do, I don't get to choose. In fact, there is no problem. What happens to these guys? Do they commute or not? Yeah, they commute. They are only creation operators. So I don't get to choose them how to, well, I get to choose how to order them. They commute, so that's no problem. Okay. Now this guy with this guy. Okay. Is this in a good order or not? In order to get 0 when we sandwich. Nope, doesn't look like that. So what do? We replace this guy by a commutator. So we are doing this term now. I had the color chalk. We could actually highlight the offending term. Is, what did we say? This guy, not this guy, with this guy is the offending term. So we can just do this and do this and compensate with a nice one. Now it looks better, right? This thing looks better. The next one would be this with this, but that looks pretty good already. And this with this. Once again, we don't get, it doesn't matter the order in which we put it, and that looks nice. Let's do the same thing for the next term. Okay, for the next term, we have, once again, 5 plus, so no problem. We get 5 plus with 5 minus. Again, that's bad. This is our offending term, so we have to fix it. And we get something that looks nice. Okay. Then the next term is this with this, which is already nice. And this with that, whose order doesn't matter. Okay. Now, let's notice 2 things. The first is that these 2 terms are identical to each other. Right? Do we have a copy of this term down here? Yeah, it's here. How about this guy? Well, that guy is here. And these guys are here. So isn't that nice? Somehow, the things that we order naturally, that have a natural order, okay, appear on both terms, right? And if you have theta of x0 minus y0 times something, times a, plus theta of y0 minus x0 times a, what do you get? A. Do you agree? Right? Well, okay, so you might worry about what happens when x0 is equal to y0, but I'm not going to worry about it. Okay, so this I'll take to be true, okay? So this is this clear to everybody? Okay, very good. Now let's use it. So how do we use it? Well, everything that appears on both loses any information about the fact that we were ordering with respect to time. So we get something that looks like, I'm going to lose all the chalk. Plus okay, plus this thing times this commutator, right? And this times this commutator. But look at what we have up there. Isn't that nice? The missing terms are exactly Now we can. The missing terms are exactly this times this, and this times this. So we can get here, and we found the missing part. They're looking like puzzle. Are you puzzled or just puzzled? Well, all we did was to find. Oh, thank you. All we did was to find the missing object, right? By being, not even by being smart, we just did it. Okay? Now, what we got here is an object where we, as we said again, it vanishes automatically when we put the expectation value with the vacuum, because every time we found annihilation operators, we put them to the right, and creation operators to the left, okay? So just as we did with the time ordering, which was something we did by hand there, right, with the step functions, we gave it a name. People also like to give a name to this operation, okay? And the name is called normal ordering the operators phi x and phi y. I would have called it natural order, but somebody invented this before. Okay, so we found our identity. The identity is that this operator is equal to the normal ordering of the operators. So the time ordering is equal to the normal ordering plus the Feynman property. Okay. Very good.
Does this have any physical meaning right now?
Not now, but you will see very soon. All right. Well, now that we got something nice like this, the natural next step is to keep playing with it and generalize it, right? So next, we can do we could do 3, but this one is going to be a little bit boring for some reason, for a reason you will see soon. So let me do 4, okay? Of course, we're not going to do the same exercise I did here. It will take a long time, but I can tell you what the answer is. The answer is going to be, you take the normal ordering of phi 1, 2, 3, and 4, okay? And you add to it, so here is where I should have introduced another piece of notation, which is going to be very useful, okay? In the end, I'm going to be able to write all terms as product of 4 fields and operations that I do on them, okay? So let me try to write this in that way before we move on and do that, okay? So what I'm going to say, or what people like to say, is that every time you see this, I'm going to define, well, actually I should define it in the other way. The definition goes like this, okay? Whatever I'm going to write here is identical to this, okay? This is just notation. You put the 2 fields, and you put something connecting them, okay? This is just notation. And it has a name. It's called a contraction. And you're going to see right now why this is useful. Because if I didn't have this notation, I wouldn't even be able to remember what the answer is of that time ordering. So this is going to be very useful. Okay? So whenever you see this, you're supposed to remove these two operators and replace them by a propagator, by a Feynman propagator. Okay? Okay, so then what is this? Well, this is equal to this normal ordering plus so once again I write phi1. Actually, I can write many of them. I'm going to write many of them. But then what I do is that I have this normal ordering term.
Why are you writing them the same thing again and again?
Because I'm going to do something to some of them now. So I'm going to take this guy, and I'm going to contract these two fields. Then I'm going to take this guy, and I'm going to contract this guy with this guy. Okay? I'm going to take this guy. I'm telling you a rule. Or I'm telling you the answer. I'm not even telling you the rule. I'm telling you the answer. You do exactly what I did there. Exactly the same calculation. You sit down for a while, and you will be able to prove that this is true.
There's 6 terms?
Exactly. There are 6 terms there. Yes? So we can talk while I write because...
Yeah, on the right you have the product of 2 operators and then this funny symbol, and on the left you just have a number. So should we interpret it as the identity on the left hand side?
Well, the Feynman propagator, yes, well, if you want.
Okay, that's what I'm trying to
Or simply the contraction of 2 operators is a number.
okay.
It's defined to be that. So, as you guessed correctly, there will be 6 terms, which are all the possible ways of contracting 2. Okay, how many I have? One more, right? But we're not done. Well, they are at different points. So this is the identity. Of course, nobody told you that x3 and x4, that they have to be distinct. They could be the same. But this identity is true for any axis. Okay? Well, I'm not done yet because what do you think is the next step? Yeah, I can only contract pairs, right? So there is 1 contraction, and now there will be 2 contractions. How many such contractions are there? Hopefully less than 6. Three. That's nice. Okay. So what is this? Well, once again, I could write my fields again up to x4, the first term. Now I can pull this out of any operators. This is not an operator. This is a number, right? That number is called Feynman propagator x1 minus x2. Then I have normal ordering of x3 and x4. plus 5 other terms that are identical, okay? Well, similar to these ones, plus these terms. But these terms are actual numbers times the identity. Yes?
So the final propagator is a Grimm's function, right?
Yes.
So you keep telling me, saying that the final propagator is a number. Actually, it's a distribution, right?
The Feynman propagator?
I mean, a Grimm's function is actually a distribution. So,
Well, any function is a distribution.
right, but I mean, how do you define and describe the two final propagators? I just can do it as if they were ordinary functions.
Yes, they are exactly, they are literally functions, right? Think about them as functions. There is no problem, okay? In fact, the Klein-Gordon operator, when it acts on them, right, it only acts on a single x at the time, right? It's a local operator. So that would be one term. This would be the next one. And the last term. Okay. All right. But now there is something fun we can do with this, which is after we work so hard to write down all these terms, we're going to take the expectation value with the vacuum. Looks like something perverse to do, but after all, that's the thing that we're after, right? So if we take the expectation value, guess what happens? This is 0, 0. All these 5 terms are 0, and all we get is this. Now, there is a nice notation for this. In fact, it's the very first example of a Feynman diagram that we're going to see. Instead of writing all this, as you can see, it's taking me a long time, we're going to do the following. We're going to denote this object by the following. We're going to say that there is a point in space-time x and a point in space-time y, and we're connecting them. Okay? So when you want to be fancy and you want to tell somebody what this is, right? Once again, very nice party conversation. You want to tell somebody what this is, then you can look very smart by saying, well, of course, you write this, and the first term will look like a propagator from 1 to 2, this. The next term will look like, so we go from 1 to 3, and the last term gives you this, okay? Now you can all guess, I hope, what this thing is going to be. Sorry?
N is even or odd?
Very good. N is even. So try to do it. Okay. So now we're ready to actually from horizontal to vertical. Oh, no, these lines can be oriented in any direction, okay? These are any two, well, in fact. Sorry. Okay, so we are ready to state
Sorry, just to ask.
which theorem.
That you would arrange them as vertices of a regular and
And then go crazy with all possible ways of fully contracting them in pairs.
that would be n minus 1 factorial.
Beats me, I don't know. You had to find out. Okay, so what does the theorem says? The theorem says that if you have the time ordering of n operators, this is equal to the normal ordering of them plus, so we're going to get terms like this with one contraction, of which there are n times n minus 1 over 2 minus 1 more terms. Okay, the minus 1 is because I already wrote this one. Okay, this is the total number of terms with one contraction. Okay, plus and so what's the total number of contractions here? So this is the total number of the first kind of contractions times the left guys and minus 1 terms. Plus all the way, all possible contractions now, 3 contractions, 4 contractions, all the way until you end up with
Where does the additional factor of a half come in? So you've got n times n minus 1 over 2. How do you get the added?
Because doing this one first and then this one later is the same as doing this one first and then doing this one later. Okay, now the last term depends on n being even or odd, of course, because if n is even, then it's the sum over all possible contractions everything is contracted, okay? And the number I'm not going to tell you, that's what you guys are going to find out if you want. And if n is odd, there will be terms. I mean, the last step would be objects where you contract everybody in pairs except for one, because it's odd, so there will be one that cannot be contracted. Now you see why I didn't discuss the case with 3 guys, because if we now take the expectation value, what do we find? 0. So from here we conclude immediately that this is 0. Okay? So I put it explicitly, the an odd number, 2n plus 1 here. Very good. So here is a point where I think I haven't decided, but I'll probably decide it if somebody does it. I'm planning to offer a reward for anybody who can prove this theorem in a nice way, in a way that somebody can actually stand down with a piece of chalk and prove it on the blackboard, okay? In, say, less than 20 minutes, okay? Given that I couldn't find it, we're not going to do it. Okay, so, sorry? No, that's not the point. The point is to do it to write it on the blackboard. That's what I haven't decided yet. The reward increases depending on the beauty of the proof, on the elegance of the proof. Yes.
We're familiar with theorem in the context of multidimensional Gaussian integration. I assume that this case is similar, but
well, in the next course you will see what the connection is. Okay.
You've already seen that in StatNet, right? You've already seen that in StatNet.
yeah. I mean, but everyone has no notion of normal ordering or time ordering.
Yes.
So in the odd case, you've written 5xn, but that's just anyone.
That's one of the terms, right? Like in the previous case, I wrote a crazy mess. That's one term plus many, many others. Yes, so there are many, many others here. Plus many, many others. I'm not telling you how many. I told you in the first two cases, but I'm not telling you how many more there are here.
Oh, sorry, but I mean, the odd one out is just any one of them.
Yeah, in the odd ones, yeah, so sorry. Here, plus many, many other. Where this guy can be anything times a mass. Yes. Okay.
So we won't go through all n terms?
Sorry?
In the additional, so do you not have phi of x1 and then another term with phi of x2?
Yes. That's what I tried to say. That the many other terms is all possible contractions, right? So at some point you will miss phi of x1, and that will be left over. At some point you will miss phi of x2, and that will be left over. Okay, just chose this one. Poor guy is always the last. So okay, very good. Now that we are experts in computing free theory correlation functions, which is, it's quite something, because we have reduced the problem of doing the interacting theory to that of computing free theory correlation functions. So we're in business. Okay, so now back to computing this out. So we have two things to do. One is to compute the numerator, and the other one is to compute the denominator. Which one to do first? Once again, I get to choose. So let's do the numerator. Let's do the more complicated one. So let's compute the numerator. Or once again, let's hope for the best. So let's take lambda to be very, very small, and we're going to expand the exponential.
How can you what physical justification do you have for using that lambda is small? What allows us to make that justification?
I thought we had this discussion already. Lambda is a marginal coupling. I don't know how to do this computation when lambda is large. Therefore, it must be small. No, of course, say when you're dealing with a complex scalar, actually two complex scalars so that they make a nice object that transforms under an SU2 in the fundamental representation of an SU2 internal symmetry. And therefore you get the Higgs sector of the standard model. These are things that you get to measure. okay? But first of all, this is a real scalar. And we have to get somewhere. We have to learn how to deal with these objects and see what they are. So let's work in the case that we can make progress, okay? Okay, so let's do it. We expand the exponential. So what do we get? We get the first term. So I'll compute the first term, you compute the next one. How about that? So this is the first term. The next term is once again, z is a real integration. Yes. Yeah, our fancy phi is a fully interacting field, right? Our phi I was this fake object, auxiliary object that we got by starting with some field configuration and acting with it with a free theory Hamiltonian, which was the wrong thing to do because we wanted really to evolve the state with the full Hamiltonian, but we didn't know how to do it. So we had to do something else. And then we reinvented this whole evolution operator by putting together the full Hamiltonian with the free theory Hamiltonian. And after a whole lecture, we found this identity.
But just from there to there, is there a difference between
from where? Oh, back to this. This is the object we're computing, right? The left-hand side is a fully interacting phi, right?
Oh, okay, okay.
That is the real object. I mean, sadly, the one that we don't know how to handle. I mean, we don't know how to deal with it explicitly. So this is correct. It's not a typo. Very good. Okay. Plus order lambda squared terms. Okay? I'm expanding the exponential. Is this clear? So let's just say that we have the exponential there. And we're running it as 1 plus minus 4 factorial. And then there will be the next term, right? So we're only keeping the 1 and this guy. The 1 gives rise to this, and the other one gives rise to this. Okay. Yes, very good. I was afraid we were going, we were not going to finish the lecture because of a technical problem. Okay. So what is this guy? Well, in our super fancy notation or Feynman's notation, it's just this. Pretty good. How about the next term? Well, the next term, we can factor out this minus I lambda 4 factorial integral d4z. All that can come out of this. And we have just something that we know, or we think we know how to compute. This object. It's just that it has 6 fields instead of 4, or 2, as we did before. But we know the rule for any number of fields. We just draw the points and connect them in all possible ways. Okay? Well, what is one possible contraction that I can make? XY looks pretty good, right? So that's one possible. So this thing gives me one possibility, which is a contraction of XY. So I'm going to write it as so I have that term times if you wish, I can still put the time ordering of this thing here. Now, what do we do with this guy? Well, this thing looks like the one we had before over here. Except there is a tiny bit of a problem, which is that all the x's are actually the same. They are z. So I have to put this guy together here, and then this guy together, and put the two things actually together. So all these points have to go to the same point. So this diagram gives rise to, so from here, I get something that looks like z. x1 and x2 must be connected to z. And x4 and x3 they also happen to be z. How about this guy? What does it give me? The same thing. And this guy? Same thing. So you get factor of 3. Sorry? This guy gives me an x, y. So this all looks very good. So this contribution, this is one contribution. Okay, what we're computing here is one contribution. So let me actually do this. There is a reason why we're going to do it like this. So I'm going to write this as minus I lambda integral d for z. And then I'm going to put this 3 here. We got 3 times this divided by 4 factorial, okay, times what we got, right? So we got delta Feynman propagator times yes, indeed. That's what we have. Okay? Very good.
Why is that funny?
Well, because it so happens to be z minus z. So this thing becomes z independent, and we have an integral over the whole space-time. But never mind. The most important thing in this equation is that this thing gives us an 8. You don't believe me? Okay. So now we move on to the next contribution. There is another class of contribution. So what's the other kind of contribution we can have? Yes, so we can contract x is z and y with another z, and 2 of these guys together, okay? That's the other possible contraction. So how do we write this down? Well, let's write it down. As I said, you have a 4 factorial minus I lambda integral d for z times delta of x minus y, minus z, y minus z, delta z minus z. What should I write there? Well, just, it's not 3 and it's not 6. Just keep saying something. What? 12, somebody said. Excellent. Why is it 12? Okay, now you got to, you said it, so you have to explain it. Who said it? You did? Okay, now you have to tell us why it's 12.
Well, you have 4 Z's to contract the X with, and then you have 3 Z's to contract the Y with.
Exactly. Okay, so this 12 is actually 4 times 3. But, as again, just as before, the most important thing about this, yes, is that this is a half, okay? And we get to draw it. So we get to draw this thing, and we draw it as x goes to z, right? Now, from z to y, and there is this funny guy that goes from z to itself. Squiggly lines. Yeah, no, we're still. Okay. So we have to introduce. So let's actually introduce some notation to make everything coherent. I said that there were 3 diagrams like this, right? But by convention, we don't put the 3 here. We simply say that you put the diagram that contributes. And these 2 objects get to be multiplied. So my symbol for multiplication would just be one guy is next to the other, okay? Implicitly, I was using that notation already. So if you see a diagram like this, and a diagram next to it with a parenthesis, it means that the 2 contributions are supposed to be multiplied, okay? Well, guess what? We did that already. In this case, where they are going vertically. So this guy times this guy, okay? Okay. So from that point of view, we can write down what the answer is. So what's the answer? So the answer to order, well, so once again, we're computing the numerator of this. Okay, yeah, I know what you can do. The numerator of this is given by xy plus xy plus order lambda squared. Excellent, very good. Question is, how about the factors? Okay, well, this looks so beautiful. It would be such a pity to pollute it with factors all over the place. Yes?
I guess the order is implicit in the number of internal terms.
The order, which order?
That's
The number, yes, very good, very good. Now we're going to see how to translate these pictures, which are Feynman diagrams, into formulas, okay? So we have to come out now with what are called Feynman rules. Okay? So where are the Feynman rules? Well, the simplest one is that every time you see something like this, you replace it by a propagator. No matter what these things are. I mean, in fact, we can call it x1 and x2. Okay? Just every time you see a line connecting 2 points, they could be the same point, you get a propagator. Every time you see something like this could be any label, of course, you replace it by minus I lambda integral d for z. That's the reason I put it. I mean, it was on purpose that I wrote the expressions exactly like that. And last but not least, you have to divide by what is called the symmetry factor. Okay, so what is the symmetry factor? That's the last thing we have to figure out, right? In one case, it was an eighth, and in the other case was a half. Once we figure that out, we're done. Let's actually do it here. So you guys never ask, I think, why did we normalize this with a 4 factorial in the first place, the interaction? We had lambda phi to the fourth power, and we put a 4 factorial. In fact, when we wrote down the general interactions, we wrote down phi to the n, and we normalized that with an n factorial. The reason is the following. Let's go back to our phi to the 4th interaction. Let's just concentrate on that, okay? So the reason is that if you have some correlation function and you have a term that looks like this, and is supposed to be contracted with external points or even internal points, it doesn't matter. Okay? So we are supposed to create diagrams by contracting objects. So these 4 legs have to go to these 4 points. How many ways are there to send these 4 guys into those 4 points? There are 4 factorial. And each of them gives the same answer. Okay? So 4 factorial ways to get the same answer. Okay? So, knowing that this is what's going to happen generically, somebody very smart decided to divide by the 4 factorial already. Okay? So this 4 factorial takes into account this redundancy. There will be 4 factorial ways to do this in general. Okay? But that's in general. Sometimes it doesn't happen. That's it. Completely. Okay. Then what is left? I mean, people call it S or 1 over S, but this S is called the symmetry factor. So what is this guy? Well, it's precisely any symmetries that your diagram has so that the contractions give you the same, the contractions that were supposed to complete the 4 factorial and that to be identified will contribute to the symmetry factor, okay? So it's hard to explain. So the best way to do it is to actually look at examples. So let's try to compute the symmetry factor of this diagram. Okay? So if the 4 points had been genetic, we would get the 4 factorial. Okay? However, now these two guys, if I flip them, I get the same diagram. Okay? So I get a factor of 2. If these guys, I flip them, I get the same diagram. So I get to lose another factor of 2. And if I send this up and this down, I get the same diagram again. So you get another factor of 2. So the symmetry factor of this diagram happens to be 8. Okay? So that's the rule. So you see that I got this. Applying my Feynman rules, I have this for the interaction vertex, 1 propagator, 2 propagators, and the symmetry factor. And I'm done, right? Okay. Who wants to give it a shot at this one? Who wants to explain what the symmetry factor of this guy is?
You can switch them around to
Now, only these two guys. These ones are fixed. Just a loop. So it's a factor of 2. So we get to divide by 1/2. Okay? Okay. The only way to figure this out really and to understand it is to play with examples. But let's actually write down what the conclusion of today is. So the conclusion is that to compute this object, all you have to do is sum over all possible diagrams with 2 external points, x and y, okay? And when you're working at order lambda to the m, with m internal points. Okay? Okay, once again, you look puzzled. So let's apply what we just learned.
I'm just wondering, so the 2 external points is
because we have only 2 external points. If we had more, we can have more, and we will. Then we can just change the rules slightly. So let's get to draw diagrams, right? So at order lambda to the 0, we have this one. Already we computed some of this. So this is a contribution to order lambda. How about lambda squared? Well, just follow the rule. How about this one? That looks fine. To order lambda square, we need two internal vertices. There they are, the propagator with two external points. So that looks very fine. Now we, of course, can have this. That also looks good. What else can we have? Which one? A line with two guys inserted there. That looks pretty good. What else? Which one? Oh, yes, that's right. So we can have, in fact, we can have, yes, that's right. We can have it here, and then this funny thing. Any other? Yes, that's right. That what you meant?
Yeah.
Are we missing anything?
The one where four connected to four.
4 connected to 4.
This one.
In the middle.
Yeah.
Which one?
This one.
Something like that. So you want? That's right. That looks like fun. Is there one more? Really? Oh, yes. Okay. Now you can go ahead and have fun, right? Trying to figure out what the symmetry factors are, and then write down the formula for each of these items. Very good. Now we have 1 more minute. Yeah, it's a pity not to do it once we have this written down here. It's just a simple observation, really. I want to rearrange these diagrams a little bit, okay? And here is how I'm going to do it. I'm going to have xy plus xy plus this guy. Sorry. Plus xy plus, you get the sequence here, right? So what I want to do, I want to write all these guys together. So okay, this is a class of diagrams, right? Now, note that there is something interesting. As an object, right, as an actual object, this thing almost looks like this. What we get by doing this times, or this guy times this guy squared, is almost that, right? But it fails to be so because there is a symmetry factor. What's a symmetry factor? Relative to the answer that I want to get. In general, it's 1 over n factorial. Here is a half. So in general, so if we have n guys, it's going to be 1 over n factorial. So what does this look like?
Can you explain why that those two are the same as that squared?
Well, look at the rules. I'm supposed to multiply this times this, and then get a symmetry factor, right? That would be a square, but the symmetry factor would be wrong to be just this. So I had to complement the symmetry factor that I have by a half. In this case, in the next one by a sixth, and so on, right? Now this looks like an exponential. So I want to rearrange these terms and say that this looks like xy times exponential of this thing. So just resum an infinite number of terms in a snap. Isn't that cool? Now I can do the same thing for these guys. How about that? Why not? I did it for these ones. So it would be this times xy times e to the, oops, this. And then I can keep going, right? Now, these diagrams that are not connected to anything, okay? Diagrams like this diagrams like this, and so on, are called vacuum diagrams. Because they really don't know anything about the external world, right? We don't have they don't know anything about the operators that we're inserting, the external points, okay? In fact, the reason they give us these funny infinities is that they don't depend on the space-time points. So they can be located at any point in space-time. So we have to integrate over the whole space-time. So that looks terrible. They are terrible, but they can be exponentiated. So that might be something good. So we keep going for all possible diagrams. So there is also this guy. Okay? And now, guess what? What I'm going to do, I'm going to write this as this diagram times the exponential over the sum over all vacuum diagrams. So somehow, all the vacuum diagrams that come together with this guy can be exponentiated, and I get a nice term. Okay? But was this guy any special? No, I could have done it to this guy. Why not, right? I could have taken this guy. In the next order, there would have been this guy. In fact, there was this guy plus this guy. There would also be this guy and two of these guys, this guy and three of these guys, and so on, okay? So I'll also have to add to this. I can add here, if I wanted, this diagram times the exponential over the sum over all vacuum diagrams. Exactly in the same way, this guy will generate the same object, okay? But why this guy and not the next one? Say this one. Okay? Well, if that's what we have here that this correlation function has factor very nicely. So there is a beautiful factorization.
But isn't that the sum over the exponential of all the bubbles?
Yeah, it's exponential of the sum over all vacuum diagrams.
Well, the other way around. Because when you pull out, you get like e to the 8 plus e to the double A.
Yeah, so it's the exponential of this guy. If I expand it, I get the first order would be this guy. The next one would be this guy times a single piece. This times this guy with a half, but this is exactly this, and so on. So this is what I get, right?
No, each term that is longer gets multiplied by the sum over all the traces diagrams. I mean, you have it in the first one with the
that
Which sum?
the e to the 8 It's x, y into the a.
Yeah, this thing here is this diagram times
The sum over the exponential.
You also have
oh, sorry.
an 8 with a double 8 and an 8 with and a vacuum.
Yes. Sorry. Yes. Exactly. There are many other terms which I didn't tell you about. Okay, so maybe yeah. So there are many other terms because now, okay, very good. So I wanted to say that this was true, but this is different from this, from what I just wrote, right? There are also cross terms. So you have this times a term that contains a product of these two guys, right? But guess what? Those guys are also there, okay? So try to go through the combinatorics and convince yourselves that precisely these guys will produce the missing diagrams that combine with this guy and only vacuum bubbles, or only vacuum diagrams, okay? So collect all vacuum diagrams times the single propagator and convince yourself that this, well, of course, I already convinced you that this was true. This class exponentiates to this, okay? The other class exponentiates to this, but there would also be mixed terms that are needed in order to get this exponential. Yes?
So when we do the sum, we're summing over all fully connected vacuum diagrams?
No, oh, you mean here?
Yes.
Yes.
I guess when you expand them out, the ones where they're not fully connected are naturally generated.
That's right. So in this sum, yes, sum over all, okay, fully connected vacuum diagrams. That's what you wanted to hit, right? That's correct, okay? So we're almost done with what I want to say because we now can write this numerator, okay, what we have there. We just found that it factorizes as the sum over all non-vacuum diagrams. Sometimes people call these ones connected, but they mean connected to external points. But I don't want to call them connected because later this week there will be diagrams that have the same name, so it will be confusing. Times exponential of the sum over all. Here we can do it, fully connected vacuum diagrams. Okay? And now we are basically done because if we look at the denominator of our formula, remember our formula has a numerator and it also has a denominator. The denominator is obtained by removing these two guys, right? The denominator is the same combinatorics. Everything is the same, except that we only get to keep the number 1 from here. So what do you think this is? Exactly. It's the exponential of the sum over all fully connected vacuum diagrams. And since we are dividing this and this, and we're putting the equal sign, this thing cancels with this, and we find that the final answer is that this object is equal, once again, to the sum over all non-vacuum diagrams.
How did the vacuum states change to omega and the phi?
how did the omega became? This is this formula over here.
Oh yeah, okay.
So we managed to compute the numerator and the denominator. Was it there? This formula, really. This is the formula we are using over there, okay? We managed to compute the numerator, we managed to compute the denominator. The numerator magically factors into two pieces, and one of the pieces happens to be identical to the denominator. So I think that means that we must be on the right track. Whenever something miraculous like this happens, shows that you are on the right track.
When did we get this funny limit at the top?
And that will be tomorrow, yes. Yes.